Hello students, welcome to Inside Physics. In this session, we will discuss some properties of crystals. Those are called lattice parameters. So, how to calculate lattice parameters and what we get if you calculate the parameters of a unit cell. So, in crystals, there are terms already we learned about the basic definitions of unit cell, basis, lattice, and everything. Here, we will find some lattice parameters which are basically related to the structure of the crystals. The first one is volume, second one coordination number, third one effective number of atoms per unit cell, effective number of atoms, fourth one atomic packing fraction, atomic packing fraction, and the fifth one density of the crystal material, the sixth one atomic radius, and the seventh one here after atomic radius we will calculate the void space. So 7. These will give you an idea of the atomic structure inside a crystal and how the atoms are arranged. The atomic arrangement gives the characteristics of the crystals. So we will see one by one how to calculate these lattice parameters. These are all together are called lattice parameters for a particular cubic structure. We have three cubic structures. The cube is a basic unit cell and we have three simple cubic, face centered cubic structure, body centered cubic structure. So here in these three cubic structures we will calculate the parameters for a simple cubic structure in this session. So relatively it is easier to calculate for simple cubic structures. And what is a cubic structure here? We will imagine a cube with a side length A or B something, whatever it is, and one by one we will try to get the idea of how we will get these parameters. So basically volume, volume of the cube. What is volume of the cube? We all know if you take the volume of the side of a cube, suppose I will take a cube of side A. So the side A is actually the length of the edge of this cube and all sides are of equal length. So volume of the cube obviously will be A cube. We all know this formula by the geometrical arrangement of this cube. So next one, coordination number. So what is the coordination number? The number of atoms, see if you consider this is a unit cell and a simple cubic structure will always have the lattice points at its corners. Okay, that is what we call it as simple cubic structure. Lattice points at the corners. How many corners it has? 8. 8 corners. So in this simple cubic structure, the lattice points are the most probable points where an atom is located. A unit cell is a building block of the crystal, we all know it. So these number of unit cells are arranged side by side and above and below and this side in a three-dimensional way, and this is a minimum size of the building block, like we arrange the bricks in a wall. So this is a unit cell with which the crystal structure is built. We need a shape for the unit cell, just like we have a shape for a rectangular box like shape for a brick. In the crystal, we will imagine a cubical unit cell, and this cell actually builds the entire crystal structure in the three-dimensional way. So volume already calculated. Coordination number means the number of atoms, the neighbor atoms of each atom. So if you can imagine that there is an atom at each corner of, there is an atom at each corner of the cube. So if you take this atom and there will be another atom in this three-dimensional picture, you need to imagine here there is another atom, there is another cubic unit cell in this side, on the back side, on the right side, on the below and the left side. So here there is one more atom here, and there is one more atom, and there is one more atom. There are, we can imagine there are three here and another three with another cubic cell on this side, on the upper side, on the right side. So on in all, the atom will be having a neighbor of 6 atoms. There are 6 neighbor atoms for each atom in a simple cubic structure. Imagine there is an atom here in this corner and there is an atom here. So each corner is having an atom. So the neighboring atoms, I will give you this picture in a three-dimensional. I will show you a three-dimensional picture here, and you can understand by that picture. So what are the number of atoms around this each atom? Okay, this is the unit cell and this is another. So in this way we can imagine a three-dimensional array of atoms which are having some neighbors. Here the coordination number of the simple cubic structure is, coordination number is equal to 6. Okay, next one, effective number of atoms in a unit cell, per unit cell. Effective number of atoms. How will you get effective number of atoms? Means, see, the contribution of an atom towards the cell. If an atom is contributing how much part of its volume towards a cubic cell. So this is the cubic unit cell, we assume, and if you say here there is this, take this corner and imagine that there is an atom here at this corner, right? So when you imagine an atom at this corner, this is contributing only 1/8 part of its volume inside this cubic cell. So imagine a sphere, a ball-like structure, and you can actually make this into 8 parts. This is only one side view, and the sphere will be other side also. You can make this into 8 parts, equal part, 8 octants. You can say one octant is present inside the cubic cell. That means only 1/8 part of the atom is contributing is its volume. 1/8 of its volume, entire volume atom is inside this cubic cell, and the other volume is actually going into the other cubic cells which are surrounded around this cubic cell. So in that way, the effective number of atoms, how many? There are 8 corners. There are 8 corners, and there will be 8 atoms and each atom contributing 1 by 8th part of its volume. So there are 8 atoms, each contributing 1 by 8. So effective atomic number will be 1. Okay. So if there is a relation to calculate this effective atomic number, effective atomic number is equal to ZB. Okay, effective number of atoms per in a body centered cubic lattice, and it is a face centered cubic lattice, and there is one more thing here, corner atoms. This is the relation to calculate the effective number of atoms per unit cell. ZB, number of atoms in a body centered structure. ZF, number of atoms. See the number of atoms in a face centered cubic structure. So here ZC, the number of corner atoms. Number of corner atoms. So in this way we will calculate the effective number of atoms in a cubic structure. Here, when you are considering the simple cubic structure, the body centered atoms is 0. There will not be any body centered atoms because we are considering the simple cubic. Simple cubic is always having the atoms at its corners only. So it is 0 plus number of face centered atoms is also 0 because it is only having the atoms at the corner. So this is 0. That means ZF by 0 by 2 is 0. Here the number of corner atoms in a simple cube is 8. So 8 by 8 is equal to 1. Effective atomic number in a simple cubic structure is nothing but 1. So okay, so I will show you a diagram, three-dimensional one, to understand the effective number of atoms. Next one, atomic packing fraction. What is atomic packing fraction? APF. Atomic packing fraction. This is given by Z small v by capital V. Okay. So effective number of atoms per unit cell. This is written as effective number of atoms into volume of the atom V, volume of the atom by volume of unit cell, which is a cubical structure. So this is the relation to calculate the atomic packing fraction. Atomic packing fraction is nothing but how much space inside a lattice cell, a cubic lattice cell, is filled with the atoms. That means the percentage of volume to the total volume of the unit cell. So in this way, how many atoms per unit cell for simple cubic structure? Z, we already calculated, it is 1. So volume of the atom. Before that, we going to volume, calculating the volume of the atom. Here small v is the volume of the atom, capital V is the volume of unit cell. So here by calculating the volume of the atom, we need the radius of the atom, right? Here it is, atomic radius. So atomic radius, how to calculate this? In a cube, the two atoms are arranged on the edge of the cube. The two atoms are arranged on the edge of the cube because they are centered at the corners. So if you take this cubical structure again and see, this is a corner and we have an atom here, this is a corner and we have an atom here. So the edge of length A, if you say, the radius of the atom is R, if you say radius and edge length. So there the atomic radius is the minimum distance between the two neighbor atoms. This is the radius. The two atoms are having a radius of R between them. This is the minimum length. This is R. This is total edge length is A. Okay. This is also R. By this what we can understand? So the edge length is equal to 2R, or the radius of an atom is equal to half of the length of the side, right? So this is what the relation we got. So with this relation, what is the radius? A by 2. So volume of the atom. Atom will be a sphere like structure, that is 4/3 pi r cube, right? And this is the small v, volume of the atom. Z we know it is 1. We already know Z is equal to 1. So by volume of the unit cell, how we will get the volume of the unit cell? We all know that in the beginning I told you it is A cube because the side of the cube is A. So by A, what is A here? 2R. So here the capital V is taken as A cube. Okay. In that sense, it is given as, so 1 into 4/3 pi r cube is 4/3 pi r cube by A cube. A is nothing but 2R. So 2R cube. 2R cube. So by this, if you calculate that relation, what we will get? You will get as pi by 6, which is equal to 0.52. Atomic packing fraction 0.52. That means almost 52% of the volume of the cubic cell, unit cell, is occupied by the atomic volume. The volume contribution of the atoms inside the cubic cell is, the fraction is 0.52, that means 52%. Okay. So this is called calculation of APF. Okay. So next one, see, we are try, this is APF. What is void space here? Void space. Void space is nothing but the remaining part. The volume contribution, the atomic volume is 52% inside the cube. If you deduct this in the entire volume, you will get the void space, that is empty space. So when there are atoms like this in a cubic structure, there is a space between the void space, the empty space between the atoms, that is called void space. How to calculate that one? Void space is equal to 1 minus atomic packing fraction into 100. Into 100 means we will get around in this percentage mode. This is 0.48, that means 48% of the space in a simple cubic structure is empty. 52% of the space in a simple cubic structure is filled with atomic volume. So in this way we have actually calculated all the 7 parameters, and we have left out with the density. We need to calculate the density of the material, which gives an idea of how close the atoms are packed. We all know that density is equal to mass per unit volume. Okay, mass per unit volume, and here we can write this formula as this relation Z into W by volume. So what is this Z and what is this W? Means Z is the effective number of atoms per unit cell, that is equal to 1, and this W is mass of each atom. That means we can write W is equal to M by Na. Okay, where M is the molecular weight of the material, okay, and Na is the Avogadro number. Then you will get the mass of each atom, okay, that is divided by the total volume. So in this way we can write Zm by V into Na, right? So what is the volume here? What is volume? Volume is nothing but, as it is given as A cube, right? Then this will be Zm into A cube into Na. So what is Z for a simple cubic structure? It is nothing but 1. So the density of a material which is having a simple cubic lattice structure is given by M by A cube into Na, where M is the molecular weight, Na Avogadro number, A cube volume of the cubic cell. This is the density calculation. So these are all the lattice parameters with which we can understand the crystal structure and its behavior and its properties. So we need these parameters to understand the properties of the crystals and their industrial usage. Okay. So in the next session we will see some more interesting topics in crystallography. Thank you. Around an atom in a simple cubic cell, there would be 6 equally spaced nearest neighbor atoms, each at a distance a from that atom. As shown in figure, 4 atoms lie in the plane of the atom, while one is vertically above it and one vertically below. Therefore, the coordination number is 6. In the three-dimensional array, each corner atom is linked to 8 surrounding cells as shown in figure. Hence, in effect, the atom contributes 1/8 of its content to a unit cell.